So let's say that we have found a linear correlation between two variables. The next thing that we'd want to do is be able to describe that relationship more thoroughly. And one way we can do that is with regression lines. So after verifying that the linear correlation between two variables is significant, the next step is determine the equation of the line that best models the data. So we've said that these two variables basically have a linear relationship, correlation. So what is that relationship? Can we quantify it? Now, it's rarely going to be exact, so we're going to need a line that does a good job of fitting those points. And that line is a regression line. And so what we can do is use this line to predict values of y for a given x. So, while we have these points here, these are not considered to be exact in any way. So we're actually going to use the line as an approximation of what we think is really the relationship between these two variables, so that now if I wanted to use this x value, I could go up to the line and find a y value for that x value, even though it wasn't even in the data set. And that's how I can approximate with it. So how do we actually come up with this line? Well, it's based on what are called residuals. For each data point, di represents the difference between the observed y value and the predicted y value for a given x value. So let's say we choose some line to approximate, to fit the data. Well, every point is likely not to every data point is likely not to fall exactly on that line. So what we're doing is figuring out how far it is. This one is below, this one is a certain distance below as well, while these two are a certain distance above. And for each one of them, we're calculating a distance, a d value, of the observed y value minus the predicted y value. So in this case, this would be the observed y value, and this would be the predicted y value. So I would get some negative difference there, whereas I would get a positive difference there. These differences are called residuals, and they can be positive, negative, or zero if you actually fell on the line itself. So what are we going to do with these residuals? Well, to get the regression line, the line also known as the line of best fit, it's the line for which the sum of the squares of the residuals is a minimum. So you're taking each residual, each of those d's, squaring it, and then adding them all up. And you want the smallest quantity that you would get out of that, which makes sense. You want the differences to be as small as possible. So now, why do we square them? Well, realize that if you took differences here, some that were negative and some that were positive, and just purely added the differences together, you're going to get a lot of canceling. And that's not really what we want to see. We don't want to think that just because we have one point that's way above and one point the same distance below, that that's really good because these ended up canceling each other by positives and negatives. So what we do is we square it, so all those residuals become positive or zero. So we're actually getting a true measure of how far everything is from the line. So the equation of a regression line for an independent variable x and dependent variable y is this here. So this shouldn't be surprising. I'm sure you've seen lines before, y equals mx plus b. Now, we do have this y hat there. Yes, we often call that y hat. It's one of the ways that's called. And this y is the predicted y value for a given x value. So it's different than the yi that would go with a certain xi. All right? These are data points. This is some x we want to know about, and this is some y hat that is the predicted value if we put in that x. And of course, just as with any line that you're familiar with, m is the slope and b is the y-intercept. So that's the line that we're searching for. Once again, I'm going to show you the way it's actually done behind the scenes. We're not going to do this type of calculation. We're going to allow some technology to do it, but so that you understand what's going on. All right, so this is the line we're after. So we need to figure out m and b, the slope and the y-intercept. All right, so here's how it would go. Here's the equation for finding out the slope based on all these data point values. And then if you wanted the y-intercept, you would use the y bar, the mean of the y values, and x bar, the mean of the x bars. In this equation here, you just found the slope before, and so this is the way that you could calculate that, where this quantity is y bar and this quantity is x bar. So once you've found m, you can calculate b, and then you get the necessary quantities to fill out your line. Note, this point, x bar, y bar, the means of the x's and the means of the y's, is always on the regression line. So what would this look like for a data set that we've studied before? If we wanted the equation of the regression line for this GDP versus emissions data, again, we saw this before and we did find that it was significant, the correlation. So here's the calculation we would go through. You had your 10 data pairs. Here's your sum of x's, sums of y's, sums of the products, and sums of x squared. Put this all in to this equation, and there's the slope that you would get, 199.5-ish. Then using that slope and a y bar and x bar, we get that as your y-intercept, your b value. And in that way, we get the regression line. And notice there is x bar, y bar, which is indeed falling right on the line of best fit. So this is a line that we're saying best approximates the linear relationship that we've established between these two variables. Now, once we have that linear relationship, we could predict y values for other x values that weren't in the data set. So the regression equation that we just found for GDP versus carbon dioxide emissions is this. Use this equation to predict the expected carbon dioxide emissions for a GDP of $1.2 trillion. Well, this is very easy once we have the regression line. All we're going to do is we're going to substitute this in as x, and that's going to give us a y hat. So there's the y hat we're calculating, there's the m, and this is the x we're going to put in, there's the b. So in for x goes 1.2, and we get this. So there is the emissions, the predicted emissions if you had gross domestic product of 1.2. All right, so notice there wasn't exactly a 1.2 in the data here. So that's what we're trying to do, is we're trying to find it for some point that's not in the data. Now, an important point about predicting y values using regression equations is that you have to be careful about what y values you try to predict based on what x values you're given. So if we go back to the line here, we see that we basically have values from a little under 1 to a little over, a little close to 5, say, as we can see in the data back here. So when we're trying to use a regression line to predict y values, we need to stay at least near this range here. We should not be going out here, some value at say 8 or so, and try to use this regression line to predict where that could be, because now we've gone a little too far away from the data set. So anything in here would probably be a meaningful approximation, and we could even go a little bit past and a little bit below, but we don't want to go too far outside the range of the data that we have, because we can't say really for sure that the trend that we have for the data given extends beyond that. So we have to be careful about that.